that the controlled nuclear fusion technology can completely solve the problem of energy in the future. Some people may be confused. It's just generating electricity with nuclear energy, which has been achieved a long time ago. And so far, we don't see any revolutionary advantages of this technology. By 2023, the proportion of nuclear power plants' power generation only accounted for about 10%. Especially with the current turbulent international situation and high energy prices, our electricity bills are obviously more expensive. And several nuclear power plant accidents have left people fearful, and anti-nuclear voices still emerge occasionally. However, people who have a little knowledge of this field have a belief-like desire for the controlled nuclear fusion technology, and even regard it as the most critical factor for the long-term survival of human civilization. Today, let's look at the potential of this technology, and build up our belief in it. First, the theoretical basis of atomic energy technology is derived from the special theory of relativity. The matter-energy equation is E equals m times c squared. Energy and matter are interchangeable. The gathering or splitting of protons and neutrons within atomic nuclei can produce new elements. At the same time, it is accompanied by loss of mass and the release of energy. What is easier to achieve is the splitting of heavy atoms, also known as nuclear fission. This can be achieved by using neutrons to hit radioactive elements that are already undergoing slow fission. This led to the creation of the atomic bomb, which uses radioactive uranium-235 or plutonium-239 as its raw material. When a neutron hits a nucleus and causes it to split, it itself releases a neutron, which then goes on to hit other nuclei, creating a chain reaction. The intensity of the reaction depends on the density of the atoms. The greater the density is, the higher the probability of being hit by a neutron, and the more intense the reaction. Thus, with a higher density, it becomes an atomic bomb, while with a lower density, it becomes a nuclear power plant. The core technology of nuclear countries is the costly uranium enrichment technology, which is why some countries cannot build nuclear bombs even though they understand the principle. And nuclear fusion is the process where two hydrogen nuclei fuse together to form a helium nucleus. This reaction results in a larger mass loss, and the energy released from the fusion reaction with the same mass of raw materials is 4 times that of the fission reaction. But the greater advantage of nuclear fusion lies in its raw materials, the isotopes of hydrogen, deuterium and tritium, which are abundantly stored in seawater. The energy produced by the fusion of deuterium and tritium, contained in 1 liter of seawater, is equivalent to that of 300 liters of gasoline. Based on the current rate of energy consumption by humans, the seawater on Earth could supply human for billions of years. Perhaps the sun will no longer exist after 5 billion years. So this can be considered an infinite energy source. Moreover, the fusion reaction does not produce any radioactivity. And its reaction product, helium, is an inert gas. It will not be as dangerous and difficult to dispose of as the current nuclear waste. The second part of Liu Cixin's novel, The Three-Body Problem, depicts a world where controlled nuclear fusion has been achieved. Firstly, all electrical appliances no longer require plugs, and wireless charging technology has become widely popularized. In fact, wireless charging technology has already been realized today, which is essentially a high-energy amplified version of wireless communication and electromagnetic waves. However, such energy dissipates severely in the form of electromagnetic waves, and we cannot afford such waste at present. But in a world where energy is almost limitless, dissipation doesn't matter. Electromagnetic induction for charging fills the entire city. Cars and bicycles fly in the air, never needing to be refueled. Huge cities have also been built underground, with their domes directly displaying images of the sky transmitted from tens of thousands of meters above. Electricity is everywhere, like air. Since fossil fuels are no longer used, the environment has almost returned to what it was before the Industrial Revolution. Everything is driven by clean electricity. Controlled nuclear fusion holds profound significance for the development of human civilization. At this moment, we can see the immense potential of controlled nuclear fusion technology, and understand that mastering it can bring us a better life. However, when we think from a different perspective, if this technology ultimately cannot be mastered by humans, what would the scenario be? After all, humans cannot solely develop on Earth. Even if energy is inexhaustible, other material resources will also become scarce at some point. The expansion of living space requires a revolution in space technology. Currently, interstellar travel using chemical fuels as propulsion can undoubtedly lead to the exhaustion of countless generations before reaching the destination. Even with sufficient fuel and oxidizer, launching these energy sources into space would potentially hinder economic development for many years. The raw materials required for nuclear fission are rare, and the energy efficiency per unit mass is too low. Therefore, nuclear fission ultimately still poses an energy problem. From this perspective, fusion engines based on controlled nuclear fusion technology are undoubtedly the most effective way for interstellar travel. After the realization of controllable nuclear fusion, human civilization can be upgraded from level 0 civilization to level 1 immediately. We will further discuss the details of cosmic civilization in the next episode. If there are no other unexpected events, such as world wars, asteroid impacts, and other disasters, and human civilization develops as usual in this tortuous way, it will take at least hundreds or even thousands of years for human civilization to upgrade it. Human footprints have spread across the entire solar system, and the interplanetary mining industry will also flourish. In the foreseeable future, we will no longer have to worry about various resources. In space, buildings do not need to be attached to anything because they are not affected by Earth's gravity. In addition, there are plenty of material resources in the solar system, and buildings can be built extremely large. Our spacecraft can be larger than a city, with various facilities inside, such as parks, hospitals, schools, and even natural landscapes like mountains, rivers, and lakes. It's almost identical to our current lifestyle. Isn't it hard to imagine? Huge ring-shaped cities rotate around giant spacecraft, generating centrifugal force similar to gravity. People living in these ring-shaped cities do not feel any weightlessness due to the effect of centrifugal force, just like living on the ground. This also aligns with our human physiological structure, as we need to live in an environment with gravity to survive healthily. Moreover, gravity can be freely adjusted according to the speed of rotation. People can also freely choose to experience weightlessness inside the spacecraft. At present, the main fuels for nuclear fusion are two isotopes of hydrogen, deuterium and tritium, as well as helium-3. Helium-3 is very scarce on Earth, but relatively abundant on the Moon. The helium-3 on the Moon is mainly brought by solar wind. However, due to the magnetic field of the Earth, helium-3 and solar wind is difficult to reach the Earth. If technology advances further in the future and the ability to constrain particles becomes stronger, we may be able to use hydrogen elements directly for nuclear fusion, just like the Sun. Some people may say that what you said is so powerful, but the energy of controllable nuclear fusion is not created out of thin air. It also requires the consumption of fuel. If our lives can reach the level you mentioned, the fuel consumption will be higher than it is now. How many times more, and more will be wasted? According to the current energy consumption, it can be used for tens of billions of years, but based on the consumption, it may not be used for many years. What if the fuel is exhausted? Will it become a new oil crisis? There are huge gas planets in our solar system like Jupiter, Saturn, Uranus, Neptune, etc., and the vast majority of these huge gas planets are composed of hydrogen. Aren't they just one giant open-pit oil field, if only a series of open-pit mining problems could be solved, which of course I recognize is a very difficult thing to do. And let's not forget that there's a sun that makes up 99.86% of the mass of the entire solar system, so if we could harness most of the sun's energy, we'd be in a second-class civilization. Of course, to realize such a future, it is impossible to solve the energy problem alone can be achieved, such as how to prevent such a large spacecraft from being hit by high-speed meteorites, how to maintain the stability of the super-large building materials do not disintegrate, nuclear fusion engines, and other similar issues. These are needed to human engineering, basic science and technology, materials and other disciplines, and then a big step forward before it can be realized. But the energy problem is definitely one of the foundations of all these problems. Without energy or not enough energy, there is no qualification to talk about such problems, let alone how to solve them. I believe that with the intelligence of mankind, as long as we don't exterminate ourselves, these problems can definitely be solved. That is why controlled nuclear fusion technology is considered a crucial factor for the long-term development of humanity. Otherwise, we would be confined to Earth, facing self-destruction through our current mutually detrimental development model. Well, after all this talk about the prospects of implementing controlled nuclear fusion technology, we must return to reality. Why haven't we used electricity generated by controlled nuclear fusion technology yet? The reason lies in the reaction conditions of nuclear fusion. The high temperature and pressure of hundreds of millions of degrees is almost the environment inside the sun. Actually, it's a bit backward to say this. The principal reaction of stars is achieved by using their huge gravity to squeeze atoms to generate high temperatures. To put it exactly, it is the fusion reaction of hydrogen atomic nuclei that generates energy. Controlled nuclear fusion technology is about simulating such an environment to make stars. The more basic principle is to get two protons as close as possible to within 1/10,000 of the diameter of an ordinary atom. Only at such a distance will the strong force within the atomic nucleus come into play, overcoming the electromagnetic repulsive force caused by the protons having the same charge. Here is a brief classification of the four fundamental forces in the universe: strong force, weak force, electromagnetic force, and gravitational force. The strong force acts within the nucleus of an atom over extremely short distances, and is the strongest of the four. It is crucial for the formation of atomic nuclei, which is why protons with positive charges can still be bound together within the nucleus. Viewers who have watched the three-body problem should all have a deep impression of the water droplet. It is created by the trisolarans by expanding the range of the strong force, thus creating the hardest known material. Against the human fleet, composed of ordinary matter, it is like cutting through watermelons and vegetables. Weak force, which exerts a restraining effect on the radioactivity of specific elements, is relatively weak. This is the reason why some elements have a half-life. And those so-called pressures, frictional forces, impact forces, etc. that we encounter in our daily life, are all macroscopic manifestations of electromagnetic forces at the microscopic level. For example, the pressure produced when people make contact is actually due to electromagnetic repulsion between electron clouds at the periphery of atoms at the microscopic level. Strictly speaking, there is no actual contact happening here. Gravitational force is the weakest among the four fundamental forces, but its effective distance is almost infinite. We experience gravity every day. Another topic to be discussed here includes temperature. The microcosmic nature of temperature is the degree of disorderly motion of particles. Nuclear fusion requires high temperature and pressure, enabling individual protons to attain more potent kinetic energy. It allows two protons to violently break through the electromagnetic repulsion and enter the range of nuclear strong force, enabling them to combine together. However, fusion reactions inside stars can be more thorough. It allows protons and neutrons, following the elemental periodic table, to fuse from hydrogen to iron. Fusion of elements above iron requires energy absorption. In fact, most elements in nature are created through stellar fusion reactions. The remaining heavier elements are produced by the explosions of massive stars and supernovae. Temperatures of hundreds of millions of degrees are difficult to achieve naturally. Even uncontrollable nuclear fusion like hydrogen bombs requires the high temperatures generated by an atomic bomb to trigger it. The current mainstream controlled nuclear fusion reaction device is the tokamak. It strips hydrogen atoms of their electrons, leaving the ions to move at high speeds under the influence of a magnetic field. By utilizing magnetic fields in different directions, it generates electric current within the plasma, achieving ohmic heating and ignition. Once the temperature reaches the reaction temperature, microwave energy is used as an input to maintain the ultra-high temperature. Under the constraint of a strong magnetic field, the plasma is kept from contacting the walls of the experimental vessel, as no known material could withstand the extreme temperatures of hundreds of millions of degrees Celsius. Last year, the tokamak device located in Hefei, China, known as the Experimental Advanced Superconducting Tokamak, EAST, achieved a sustained fusion reaction lasting 101.2 seconds, breaking a world record. The reason for the duration of only 101.2 seconds is that achieving and maintaining such high temperatures and pressures is extremely difficult. The peripheral confinement magnetic field requires superconducting materials that operate near absolute zero, truly representing the ultimate contrast of fire and ice. When such immense energy is applied to such a small scale, even the highest precision currently available seems incredibly crude. How desirable a world illuminated by fusion reactions would be. However, the path to such a wonderful future is always fraught with twists and turns. Despite the geographical technical challenges we have discussed, international political factors may not necessarily be smooth sailing. If controlled nuclear fusion is achieved, it will undoubtedly affect the current vested interest groups. Will they readily give up this lucrative business without making any substantial investment? Of course, obstacles to development will not prevent progress.